In this video, we examine the idea of sample proportions, how we calculate them, and how we justify the accuracy of our results. Some examples of sample proportions might be situations where actually taking a survey of everybody in our region or country is too expensive or too time-consuming. Some examples of questions here are how many people or what proportion of people in Australia are dog owners, and what proportion of people use public transport to go to work. Questions such as these might assist in the planning and development of infrastructure within a country. So once we consider our sample, we need to ask ourselves some questions about its reliability. How does it compare with other samples? And how does it also compare with the proportion in the entire population? To assist us to answer these questions and look at the process of sample proportions, we'll look at a simple activity. What we'll do is we'll roll a 6-sided dice 5 times and consider the proportion of odd numbers. And we'll take 30 samples of that situation. We'll then repeat it, but this time we'll roll the dice 10 times and look at 30 samples of that. And then we'll repeat the process again, rolling the dice 20 times and looking at 30 samples of that situation. The purpose behind this is to see if we can see some pattern occurring with regards to the size of our sample and also the reliability. So does taking 20 dice rolls give us a better indicator of a sample proportion than 5 dice rolls? Let's have a look. In the first instance, we'll go with 5 dice rolls and we'll repeat this experiment 30 times. To do this, what we'll use is a simulation on a class pad. The one that I'm using here is a Casio class pad. You can see here from the instruction on the screen that I'm going to take a random list of numbers, in fact 5 of them, and they vary as whole numbers between 1 and 6 inclusive. And the first sample I've got here has got 1 odd number out of 5. Now to do the calculations quickly for the rest of our 29 samples, what I'll do is instruct the calculator to take a modulus of all of the random numbers we've generated. So in this case we're dividing by 2 and seeing what the remainder is. If the remainder is 0, it's an even number. If the remainder is 1, it's an odd number. So we can quickly see from our list that we've got 1 number which is odd. And to take it a step further, what we will do is sum those results and divide it by 5, and that gives us a proportion of odd numbers. So that's our first sample proportion, and what we're going to do is repeat this over and over again so that we end up with 30 numbers representing the proportion of odd numbers in our sample of size 5. Now let's have a look at the graphing process of these sample proportions, and we sped this up by doing all of the calculations beforehand. The horizontal axis of the graph represents all of the sample proportions. So in the case of a sample size of 5, the only options are 0, 0.2, 0.4, 0.6, 0.8 and 1. On the vertical axis, we have the number of samples. You'll notice as we go through this graphing process that on the horizontal axis there's a P with a little hat on it, and that represents the sample proportions. So let's have a look at our results. We can see from our table that we've got 2 instances where we had a sample proportion of 0. Now if you roll the dice 5 times, you'd expect that on average 2.5 out of 5, in other words half the times, you get an odd number, and 2.5 out of 5 is 0.5. You can see that the most common occurrences for our sample proportions were 0.4 and 0.6. They both occurred on 8 occasions. In terms of a summary of results, with a sample size 5, the mean sample proportion was 0.4733, and again we'd expect it to be 0.5, and the standard deviation, which measures the spread of the sample proportions, was 0.2502. Now let's extend our activity by repeating the same process, but this time what we'll do is we'll have a sample size 10, and we'll repeat this to achieve 30 samples. Given that there are 10 rolls of the dice, our possible sample proportions this time start at 0, going up by 0.1. Here's our table. The smallest sample proportion that we achieved was 0.3, and that occurred 8 times, and the largest was 0.9, occurring twice. Let's have a look at a summary of those statistics. If we roll the dice 10 times, we expect 5 out of 10 to be odd, and we can see here that the mean is 0.5233, so quite close to 0.5, but the standard deviation has dropped quite a lot, so it's 0.1745. Now let's repeat the process. This time we'll roll the dice 20 times. So our possible solutions now differ by 0.05. So here's a summary of our results. The smallest sample proportion that we achieved was 0.35, and that occurred 3 times, and the largest was 0.75, which occurred once. What's of interest is that we seem to be getting more scores in the middle. If we look at our previous tables, there appears to be a larger frequency for the sample proportions close to 0.5. And likewise, if we look at our summary statistics, we'll notice that the standard deviation for a sample size 20 is considerably lower than our previous cases. In this case, it's 0.0998. And when we originally started with a sample size of 5, the standard deviation was 0.2502. So there does appear to be some evidence at this stage that the standard deviation, or in fact the spread of these sample proportions, does decrease as the sample size increases. So these tables represent what we'd say is experimental data. We've done a simulation, in fact 3 simulations, we've gone through and provided these results. But what does the theoretical probability suggest should occur? Well, let's have a look, keeping in mind that when we've got dice being rolled, and we're investigating the chance of the dice occurring with an odd number or an even number, we can tie this in with the binomial distribution. So in the binomial distribution, we have an expected value given as NP. And to take this a bit further, if we want to work out a proportion, what we do is we say, well, it's NP divided by N. So for example, in the case of our odd numbers, the expected number of odd numbers out of 5 is 2.5. But as a proportion of odd numbers, that's 2.5 divided by 5, or in other words, a half. In summary, the expected proportion, you can see from this formula on the screen, is P. Well, now let's have a look at the standard deviation that we expect to occur for our sample proportions. For a binomial distribution, the standard deviation is NP multiplied by 1 minus P, all inside a square root. But for our proportions, we need to divide that by N. With some algebraic simplification, we can see that the square root will still have P and 1 minus P in it. We'll leave it in the brackets, we won't expand that. But the square root of N divided by N will leave a square root of N on the bottom line of the fraction. We'll put all of that inside one square root, so it's the standard deviation for our sample proportions equaling to, in a square root, P bracket 1 minus P all over N. So these two statistics, that's the mean of P for our sample proportions and the standard deviation that you can see on the screen, contribute to this result. As our sample size N increases, the distribution of our sample proportions start to approach that of a normal distribution. Now that may not be immediately obvious, but let's have a look at our graphs and the results we've got earlier. You'll notice that as the sample size increases from 5 through to 10 and then 20, gradually what occurs is we start to get the formation of the bell shape familiar with the normal distribution. We start to get more of our sample proportions in the middle. In other words, in this case, we were expecting 0.5 for the proportion of odds, and our standard deviation decreases as we also see the sample size increase. So we see more of our scores centered around our mean. So the question then becomes, at what stage can we become confident about applying the normal distribution to this situation? As a guide, if we were to multiply N and P together, and they're greater than 10, and also multiply N by 1 minus P, and that's greater than 10, that would give us confidence to apply the normal approximation for these sample proportions. Now let's have a look at the theoretical model in terms of the mean and standard deviation and see how it compares to our experimental data. We can see in the table below where our experimental data is from our previous random samples, the standard deviation is gradually decreasing, and there does appear to be a relatively close match to the theoretical model. Of course, the theoretical model expects the mean or the sample proportions for the odds to be 0.5 consistently. Let's now have a look at an example and see how we use the notion of sample proportions and the normal distribution to justify the question being asked. In this case, we're being asked to see if something is extremely unlikely, and we know that based on the normal distribution, 99.7% of all data is within 3 standard deviations of its mean. In this question, we're told that 8% of matches taken from a matchbox would be unable to light. In other words, 92% should work. And we're being asked, is it extremely unlikely to find 23 out of 155 matches that do not light? So what we need to do is consider our sample proportion, in this case 23 out of 155, and see how it compares to the theory. So based on what's expected, we know that 8% of matches are unable to light. As a proportion, that's 0.08. And we can use that same value and also our sample size, in this case of 155, to determine the standard deviation for our sample proportions. When you calculate those two values and apply the idea of a normal distribution, we can see that we have a normal distribution with a mean of 0.08 and 0.0218 for the standard deviation, and that represents a proportion of matches that do not light. The idea now would be to consider 3 standard deviations either side of 0.08 and see if our sample proportion fits within that range. If it does, then perhaps that's a reasonable sample proportion. If it doesn't, we can say it's extremely unlikely. So in this case, our mean is 0.08, and we're going to subtract 3 lots of the standard deviation away from that. That'll be the lower end of our range of values, and we'll also add 3 standard deviations to 0.08. When we do that, we see that our range of values is 0.0146 to 0.1454. So what this means is that if we take a sample of matches and we look at the proportion of those that do not light, 99.7% of the time that proportion will be between 0.0146 and 0.1454. So we need to consider what is the decimal proportion of 23 out of 155 and see if this is extremely unlikely. So when we determine the decimal value of 23 over 155, we get 0.1484. This is just outside the range of values. So this sample proportion does appear to be extremely unlikely. So that'll be our summary answer, but what we should always do as well after this is make sure we make a comment to see if we're happy that it's valid to apply the normal distribution. The test we did beforehand was to multiply the p-value, in this case 0.08, by the number in the sample, 155. In this case, that comes to 12.4. Likewise, we multiply the complement of 0.08, so 0.92 by 155, and that also needs to exceed 10. If both of those cases occur, then we can be satisfied that the normal distribution is a good application for our test here with the sample proportions.